Okay, today we're going to talk about reactions in aqueous solutions, and it's very important to understand reactions in aqueous solutions because a lot of the reactions we encounter in nature do happen in aqueous solutions. Okay, so let's just do a little bit of a review about what the solution process involves. So what happens when you put something in water? In a liquid such as water, you put something else. The substance that you put in the water is called the solute. Okay. Oops, sorry. And your solute is a substance that's either made up of ions or molecules. So the ions and the molecules in your solute will be dispersed in the water. Each one is going to be surrounded by water molecules. Now, the liquid itself, the water, is called the solvent. Okay, and like I said, the solute particles, the ions or the molecules from the solute, okay, are surrounded by solvent molecules. So this process where you have an ion surrounded by water molecules, so if I represent these water molecules by these, then, and this would be your ion right here. Okay, so the process of surrounding an ion or a molecule by solvent molecules is called solvation. So we say your ion or your molecule is solvated. And if that solvent happens to be water, then the solvation process is also known as a hydration process. So hydration refers to this process where an ion or a molecule is surrounded by water molecules. Okay, so that's solvation. And let me see if I can get you some visualizations to help out, to remind you of what's involved there. So if you go to phet.colorado.edu, it's taking a while to get there. Okay, looks like the site's down, so let's just let me see if I can find it in the files that I previously downloaded. Let me see. No, I don't have them here. Okay, so let's just continue on then. I'll pick up that animation later, or you can watch it on the Moodle site. Okay, so let's just do a quick check here. Let's say you have here a pictorial representation of an aqueous solution of calcium chloride. Which of these? So this is a clicker question. Which of these represents an aqueous solution of calcium chloride? So imagine your circles as solute particles, and then the gray shaded area represents the liquid, which would be the water. Is it A, B, C, or D? Okay, so we have 7 people picked A, 2 people picked B, 3 people picked D. Okay, and so let's see. Uh, Let me give you a review about calcium chloride. If you look at the formula, calcium chloride, you'll notice calcium is uh, a metallic element, right? So if you find it in compounds, you expect it to be positively charged. So this calcium chloride is an ionic compound. So if it happens to dissolve in water, you would expect it to spread out into ions. Each ion is going to be separate from the other ions. So your calcium ions would be separated from your chloride ions. So one formula unit of calcium chloride will give you one positive ion and two negative ions. So it's going to give you three particles in water, calcium and two chlorides. Okay, each one of these will be surrounded by water molecules. Of course, you have a whole bunch of them. Each one would be separated by, will be surrounded by water molecules. It will be solvated. So given that new information now, can we retake the poll and see what the correct answer is? Okay, very good. Correct answer is C. Okay, and which one of these will be the calcium? There's twice as many chlorides as there are calciums, right? So these would be your chlorides, okay? And the black circles would be, the filled circles would be your calcium ions. Okay, so that's what happens to calcium chloride in water. You put it in water, it spreads out, all the ions are dispersed, each one is individually hydrated. So we can say, we can represent this process by saying, okay, if I were to put calcium chloride solid in water, so CaCl2S, I can draw an arrow, I can say it would be in aqueous solution. Okay, this is what we would call a molecular equation. It's a representation of the dissolution process. It's called a molecular equation because you're writing CaCl2 as though it's made up of molecules. It's not. So a more accurate or a much better way of representing what actually happens is to say your calcium chloride solid is dispersed in water. So it will give you calcium ions, aqueous, plus two chloride ions, aqueous. Okay? So both of these represent the dissolution of calcium chloride in water. This first one right here is what we would call our molecular equation. The second one here is what we call our ionic equation. Okay. The ionic equation is really a better representation of what actually happens, although there's nothing wrong with writing it using the molecular equation. The ionic equation just happens to be a better description of what actually happens. Okay. So a little bit of a review about electrolytes and non-electrolytes. We said pure water is a very poor conductor of electricity. Okay. But there are substances that when you dissolve them in water produce ions. Okay, so when you produce ions in aqueous solution, that you end up with a solution that conducts electricity, and these substances are what we call electrolytes. And ionic compounds are strong electrolytes. If you dissolve them in water, they're going to spread out into separate ions. Positive and negative ions will be separated. And so that allows your solution, the resulting solution, to conduct electricity. Most molecular compounds, on the other hand, are non-electrolytes. So that's why earlier in the semester we emphasized an important skill for you to be able to tell apart just by looking at the name or the formula whether a compound is ionic or molecular. Okay, so that's one of these things you can predict based on the nature of the compound. Okay. Now, it is possible for molecular compounds to produce solutions that conduct electricity. So there are some molecular compounds that we would consider to be electrolytes, and these are the acids and the bases. And the reason they are electrolytes is because they actually react with the water to produce ions. So if you have an acid, okay, a molecular compound that reacts with water to produce hydronium ions, H3O+, often abbreviated as H+, okay? It's really H+ from the acid attaching itself to a water molecule That gives you H3O plus. Okay, so this H plus right here, this will come from the acid molecule. It breaks off from an acid molecule. It will give you H3O plus ions. Okay, so this is what you would call a hydronium ion, H3O plus. And so those compounds, we call them acids, and there are compounds that will react with water to produce hydroxide ions, and those are called bases. So acids and bases are, you can have molecular compounds that can react with water to produce hydronium and hydroxide. Those compounds are referred to as acids and bases. Okay? So an acid then, we can represent an acid by the generic formula HX. Okay, where X could be anything. Okay, so what happens is if you have an acid, you put it in water, the H from the acid breaks off, and so your acid breaks off into H plus plus X minus. Notice that if a plus breaks off, what's left behind has a negative charge. So that H plus attaches itself to a water molecule, gives you hydronium ion, and what's left behind is a negative ion. Okay, so this is the reaction with water, and we can abbreviate that reaction by writing it this way. So you can just you can omit the water, and instead of writing H3O plus, you can write H plus. So this reaction is really just an abbreviation for that more complete description of what actually happens in water. Okay, and like I said, H3O plus is called the hydronium ion, hydronium. And H plus is also commonly referred to as just a proton. Why is it a proton? If you recall, a hydrogen atom consists of one proton and one electron, right? One electron going around, and you have one proton. So that positive charge in the nucleus of a hydrogen atom is a proton. So if you remove one electron, okay, the plus charge means one electron gone. So if that electron around the proton is gone, you're just left with a proton. So H plus, the ion, is called a proton. So you can also say that an acid is a proton donor. Here, your HX, your acid, you can think of it as having donated an H plus to a water molecule. So this H plus right here, oops, this H plus from the HX got donated to the water molecule to give you hydronium ion. Okay, so we can define an acid molecule then, or an ion that has a hydrogen that can break off as a proton, as a proton donor. So that's an acid. An acid is a proton donor. We say that HX in this case is ionized in the water. So HX, which is a neutral molecule, okay, when it donates a proton, it's ionized. It forms ions. So we say HX is the acid, and the ion that's left behind after it donates a proton, okay, in this case would be X minus. That's called the conjugate base of HX. So if you have an acid, it donates a proton to the water molecule. The acid is called a proton donor. Okay, and what's left behind, in this case X minus, would be called the conjugate base. So here's a question that says, write the chemical equation for the ionization of HF in water. So then you're going to say, all right, HF is an acid, hydrogen fluoride. So it ionizes in water, so if it reacts with a water molecule. Then your water molecule picks up a proton from the HF. That gives you H3O plus. And what's left behind? You just have fluorine with a negative charge, so a fluoride ion is left behind. So this would be the chemical equation for the ionization of HF in water. Okay, so when an acid ionizes in water, another way of saying that is the acid donates a proton to a water molecule. Okay, now HF has only one hydrogen that it can donate to water, so HF is also known as a monoprotic acid. Okay, so this is an example of what we call a monoprotic acid. Somebody has a question? Okay. Now, bases, on the other hand, okay, if you have a molecule that can react with water to form hydroxide, then you refer to that molecule as a base. So if we represent that by our generic formula as just, let's say, letter B. This B here is not boron, okay? It's just a generic symbol for a base. So if you have a base, okay, it will pick up a proton from a water molecule. So okay, so a hydrogen from a water molecule can be picked up by another molecule. So B, here your base, would combine with that H plus from water, would give you BH plus. So what happens when your H plus is removed from your water? You're left behind with a hydroxide ion. So if you have a molecule that can pick up a proton from water molecules and produce hydroxide ions, then you say that molecule is a base. Okay? Typically, the kinds of molecules that are able to pull an H plus ion away from water are those that have nitrogen in them that have a lone pair. Okay? Remember, a lone pair is an unshared pair of molecules. So ammonia, for example, NH3, is an example of a base. Okay? So what does a base do? It pulls a proton away from water, so we can define a base as a proton acceptor. So here your base accepted a proton from water, gives you BH plus. Now, once your base accepts a proton, it forms, okay, this is now B is now, after accepting a proton, it's now BH plus. What you get is called the conjugate acid of the base. So B is the base, add one more proton to it, you get what's called the conjugate acid of the base. All right. So in water, protons get transferred from molecule to molecule. You can think of it this way. And so that's how you form hydrogen ions, hydronium ions, and hydroxide ions. In fact, okay, water itself, okay, to a certain extent, react with each other, molecules of water. So you can have a water molecule pull a proton away from another water molecule. That gives you hydronium and hydroxide ions. So if you have pure water, you actually do have some hydronium and hydroxide ion there, but those concentrations are very low and they are equal in pure water. Each one of these will be 10 to the negative 7 moles per liter. Okay, and so 10 to the negative 7 molar. So pure water will have equal amounts of hydronium ion and hydroxide ion. It's when you add something else that would alter that balance of hydronium and hydroxide ions that you end up with what we would call an acidic or a basic solution. All right. So this transfer of proton from one water molecule to another, that's called autoionization of water. And we'll learn more about that in a later chapter. Okay? Here's a question here. What would be the chemical equation for the reaction of NH3 with water? Well, NH3, like I said, is a base. So if you write NH3, and you were to react that with water, if NH3 is a base, then it pulls a proton away from water. So what happens when you add an H plus to NH3? You have one extra proton, so that's now going to be NH4 with a positive charge. So that's ammonium ion. Okay? And what's left behind from the water? You get hydroxide ion. So this will explain why a solution of ammonia in water is basic. Okay? NH3 is ammonia. If you put it in water, you get a basic solution because the ammonia molecules react with water to give you hydroxide ions. Now, most acids and bases, molecular acids and bases, are weak. Okay? They're weak electrolytes. So they're weak electrolytes, so they're weak acids and weak bases. When you say they are weak, okay, what we really mean is that at any given point in time, at any given instant, only a very small fraction of these molecules are actually ionized. Okay? Most acids and bases are weak electrolytes. And there are only 6 acids, 6 of these molecular acids and bases, all of them acids, that are known to be strong electrolytes. So we refer to these as your strong acids. Okay, so HCl, hydrochloric acid, HBr, hydrobromic acid, HI, hydroiodic acid, HNO3, that's nitric acid, HClO4, perchloric acid, and H2SO4, sulfuric acid. So those are the only known strong acids in water. All other acids are weak electrolytes. They're weak acids. At any given time, only a small fraction of those acids are ionized in water. Okay? So for example, if you were to write the ionization of HF in water, we did this earlier. HF plus H2O gives you H3O plus F minus. It's customary to actually draw a double-headed arrow here, one pointing forward, one pointing in reverse, to indicate that at any given time, most of your HF are actually intact. Only a very small fraction of these molecules have actually reacted with water. And this reaction, the proton transfer, is reversible. Okay, so protons hop from a water molecule to another water molecule. It can hop from an H3O plus or an F minus to give you back HF and H2O. And so at any given instant, more of your HF are actually in the molecular, what we call the molecular form, as opposed to the ionized form. That's what a weak acid is. So here's a concept test, a concept question, checking to see if you understand the concept of a strong acid and a weak acid. If you remember, HCl is one of our 6 known strong acids, and HF is a weak acid. Okay, so this is a strong acid, and HF is a weak acid. Okay, so which of the figures below, A or B, best represent aqueous solutions of HF and HCl? So is A the best representation for both, or is it B, or is A better represents HF and B better represents HCl, or is it HF better represented by figure B and HCl better represented by figure A? So if you were to put HF and HCl in water, what would they look like if you could see those ions or molecules? A, B, C, or D? Most said D. HF is A, very good, and HCl is B. So this is completely ionized. Okay, all the molecules are broken up into ions. Here, most of the molecules, in fact, this one shows everything is still intact. Okay, there's a very, very small fraction of those HF molecules that are actually broken up. That's why I drew it like this. There isn't any molecule that's actually broken up in this figure, because I've only got like 1, 2, 3, 4, 5, 6, 7, 8, 9 molecules in there. If you've got billions of molecules in there, then you might have maybe thousands or molecules that are broken up into ions. So that's correct. All right. Now, the chemical equation for the dissolution of substances in water, you can write it by writing the formula of the solute, and then you indicate the physical state, whether it's solid, liquid, or gas. Then you draw an arrow, and then on the right-hand side, you write the formula of the solute, and then you write AQ. Like the example I showed you earlier is CaCl2. If you were to put it in water, okay, this represents the dissolution of calcium chloride. You just change the label from S to AQ. But like I said, an ionic equation is a preferred way of writing the chemical equation, because it's a more descriptive way of it's a more accurate way of describing what actually happens. So we know that if you have calcium chloride, Okay, if you were to put it in water, there's really is no such thing as CaCl2 molecules in water. So it's really calcium ions in water and 2 chloride ions from each calcium chloride in water. Okay, so this would be what we would call an ionic equation, and this thing right here is what you would call your molecular equation or complete formula equation. You're writing the ions as one whole thing, as though it's a molecule. Okay. Now, if your solute happens to be insoluble, what does insoluble mean? That means it doesn't dissolve in water. Okay, then use a double-headed arrow instead. Now, the question is, okay, how can we represent, why are we talking about the dissolution of something that's insoluble? When we say something is insoluble, okay, we don't really mean zero solubility. What we actually mean is very low solubility. This is not the same, this is not zero, okay? So this actually means very low solubility. But when we say the solubility is very low, we just say it's insoluble. For practical purposes, we say there's hardly any of it that will dissolve, but you do get some of it in solution, and so you still use ionic equation if it is a strong electrolyte, but then you have to indicate a double arrow instead to indicate that your solute is not soluble in water. Okay, let me see if show you a few examples here. Write the equation for the dissolution of the following in water. Solid barium chloride. Then you say BaCl2 solid. If you put it in water, okay, then you get BaCl2 aqueous. Okay, this is the molecular equation. The ionic equation would be BaCl2 solid yields barium ions, aqueous, plus 2 chloride ions, aqueous. So this is what you would call your ionic equation. It's a more accurate way of describing what happens. Let's look at the second one here. It says glucose, solid glucose, C6H12O6. Now, what do we know about glucose? Based on the formula, C6H12O6, okay, it will dissolve in water, so you write it as C6H12O6 aqueous. This is the dissolution reaction for glucose in water, and we don't have an ionic equation for this because glucose is a molecular compound, right? This is molecular. If you put it in water, the molecules are not going to break apart into ions. They will stay intact as molecules. So each glucose molecule will just be surrounded by water molecules. Okay? So this is the only way to represent the dissolution of glucose in water. So molecular compound, whatever you have, solid or liquid, you put it in water, you just write the same formula and you write parentheses AQ to indicate that it's in water. What about calcium carbonate, chalk? What do we know about chalk? Have you ever tried mixing chalk with water? In one of your labs, you'll do this. And you'll find that if you mix chalk with water, it's not going to dissolve. So you're going to say calcium carbonate gives you calcium carbonate aqueous, solid to aqueous. Okay, we say it's insoluble, but what we really mean is the solubility is very low. So it's customary to indicate that by drawing a double arrow. So one arrow pointing to the right and one arrow pointing to the left. Okay, because it's insoluble in water. Now, calcium carbonate in water, okay, is not going to be pairs of calcium and carbonate ions. They're all going to be dispersed. Each ion is going to be surrounded by water molecules. So this is actually much better represented by writing it separately. Calcium ions, aqueous, plus carbonate ions, aqueous. So anytime you have an ionic compound in water, you have to write them separately. Okay, so I can rewrite this. CaCO3 solid, double arrow, and then calcium ions plus carbonate ions. So what we have here is what you would call your ionic equation. This is a more descriptive way, the more accurate way of describing what happens when you mix calcium carbonate with water. A little bit of it dissolves, and whatever little bit of it dissolves are in the form of ions that are individually surrounded by water molecules, individually hydrated. What about this next one right here, hydrogen chloride gas? Well, hydrogen chloride is a gas, pure hydrogen chloride, but if you mix it with water, what happens? Well, HCl gas. If you mix it with water, you get HCl aqueous. Okay, that's your molecular equation. Why do you call it the molecular equation? Because we can write this another way. We know that HCl is a strong acid. So it's actually better to write it as H plus aqueous plus chloride aqueous. So you say HCl gas yields H plus aqueous plus Cl minus aqueous. This is your ionic equation for the dissolution of hydrochloric acid in water. Okay? HCl is hydrogen chloride. How about acetic acid? Acetic acid is pure acetic acid is a liquid. So an acetic acid, the formula for acetic acid is HC2H3O2, hydrogen acetate. Okay, so HC2H3O2. It's also known as glacial acetic acid, the pure liquid. You put it in water, you get HC2H3O2 aqueous. Okay. Do I need to split this up into ions? The answer is no, because this is a weak acid. Only a very small fraction of these are actually ionized in water. So the dissolution of liquid acetic acid in water is represented by this molecular equation right here. Okay? Now, the molecule itself, once it gets into water, reacts to a certain extent, a very slight extent with water to give you your hydronium ions. So once you get your acetic acid molecules in water, okay, then you say HC2H3O2 aqueous. They can react with water molecules, okay, to give you so this proton right here is going to be donated to a water molecule, so that gives you hydronium ion, and then what's left behind is your acetate ion, which is C2H3O2 with a -1 charge. Now, acetic acid is a weak acid, right? It's not one of the 6 strong acids, so to indicate that you're dealing with a weak acid, it's customary to just draw a double-headed arrow, okay? So this would be the ionization of the acid in water. This first reaction, the first equation we have here is the dissolution. So this is the dissolution in water. And this is the ionization in water. Ionization in water of your acetic acid. Okay? Same thing with ammonia. Ammonia is a weak base. So ammonia, NH3, gaseous ammonia. If you were to dissolve it in water, then you say ammonia gas becomes NH3 aqueous. And since ammonia is a weak electrolyte, this is the equation for the dissolution of ammonia in water. Okay? You don't split it up into ions because your ammonia will not split up into ions in water. What it does though, once it gets in the water, your ammonia will pick up a proton from a water molecule. So it's already in water. Once it's in water, it will react with a water molecule to give you ammonium ion plus hydroxide ion. But ammonia is a weak base, so this happens to a very slight extent. At any given instant, most of your molecules are actually going to be in this form. So that's why we draw a double-headed arrow right here. By the way, you can draw your two arrows like this, or you can draw it like that. Okay, this is the most common way you see it in textbooks. All right. So based on that, let's look at these questions. Which of these best represents the dissolution of calcium chloride solid in water? Is it A, B, or C? The best representation for the dissolution of calcium chloride solid in water. Most said D. Or was that from before? Okay, I'm sorry. Okay, 4 people said A, 2 people said B, and 5 people said C. Okay, correct answer is A. Okay, most of you realize you do need to write this in ionic form. B is, there's nothing wrong with B, but it's better to use, but this is what you would call a molecular equation. Okay, but that's not the best way to represent what happens. What happens is your calcium chloride is going to give you calcium ions and 2 chloride ions, 2 separate chloride ions. Okay, there is no known diatomic chlorine, diatomic ion with 2 chlorines with a -2 charge. So you kind of have to be familiar with your monatomic ions and your polyatomic ions. Okay, so you get 2 chloride ions from every calcium chloride formula unit. So the best answer is A. How about this one? Which of the following best represents the dissolution of methanol, CH3OH, which is a liquid in pure form? If you put it in water, what is the best representation for the dissolution of methanol in water? Is it A, B, C, or D? Okay, very good. It's a molecular compound. Most of those molecules will remain intact. We know that because it's based on the way this one's written, CH3OH. That's not an acid or a base. Okay, if it's an acid, you would usually write it as H something. And the only base I've taught you so far, the only base you really need to know at this point, that's molecular base, is NH3. Okay, you'll encounter other bases sometime later. So if it's a molecular compound, well, even if it's base, it's still going to be a weak electrolyte, so it has to remain intact. Okay, most of it will remain intact in water. Okay, so if you have a molecular compound in water, your best bet is not to break it up into ions unless you know it's one of the 6 known strong acids. So let's look at this one again, which let's look at another question again. And this one, you have nitric acid. HNO3 in water. What's the best way to represent the ionization of the acid in water? So you have to kind of go back to your list of strong acids. Is this one of the strong acids? And what does an acid do in water? Okay, 5 people said B, and 4 people said C. All right. Okay, at least you know that if you have an acid, you should get an H plus, so that's good. All right, and you kind of have to know that nitrate is a polyatomic ion, so that's one whole unit right there. So the correct answer is B. You're not gonna get, there are no nitride or oxide ions in water. Okay, so usually when you see acids written this way, okay, think of it as HX. Okay, so you have your H, and then what's left behind is X minus when your H plus breaks off. So when the hydrogen breaks off from your nitrate, okay, the proton breaks off. So take out the H, and what's left behind is going to end up with a negative charge. So nitrate ion. All right, let's talk about solubility since we talked about soluble and insoluble solutes earlier. Now, how do you actually determine solubility in the lab? In one of the labs that you'll be doing, you'll be testing solubility, and a simple procedure you do in the lab is you take about a sample of the substance you want to test, about the size of a grain of rice, okay, and mix that with about 5 mils of water. So about a teaspoon of water, that's about 5 milliliters. So put that in a test tube. So you have your water in a test tube, about 5 mils of it, 5 milliliters. And then put a little pinch of whatever you're trying to test. So about the size of a grain of rice. They used to say take a pinch, but we don't want you touching chemicals in the lab. So you'll actually have to use a spatula to do that. All right. So you mix that with water, and then you shake well. Okay. And if you see something that's cloudy, what that's telling you is it's not blending with the water, so your substance is insoluble. Okay, if you let it sit, eventually that cloudiness is going to clear. Your substance, which is insoluble, is going to settle to the bottom of your test tube. So you have a substance that we would call insoluble in water. And keep in mind, when we say insoluble, we don't mean zero solubility. What we mean is very, very low solubility. Now, if you mix it with water and you end up with a clear, homogeneous mixture, then that means your substance is soluble. Okay, now, when we say clear here, it's common mistake students make in the lab. When we say clear, okay, it means you can see through it. It doesn't have to be colorless. Okay, so if you mix, students sometimes associate the word clear with colorless. It could be blue, but if you can see through it, it's uniform throughout. It's clear. It's transparent. Then that's what we mean by clear. Okay. So, and one other thing, a common mistake students make in the lab is to describe something clear as white. White is not clear. Okay, clear means you can see through it. White is white. You can actually see white. All right. So here's how do you determine if an ionic compound is soluble or not? You can do that in the lab, but if you're not in the lab, you can make predictions. You can make predictions based on some rules. And these are empirical rules, which means that they're based on experimental data, so they've been summarized. And so the rules that you'll see depends on what textbook you're looking at, okay, because it depends on what the author considers as common, okay. So there's some textbooks that include more compounds than others. But basically, these rules will typically tell us, okay, what's always soluble among the common ones, among the common ionic compounds. And then a second rule will tell you what's usually soluble and what are the exceptions. And then a third rule will pretty much tell you that everything else is, that's if rule 1 and rule 2 don't apply, then everything else is insoluble, but it will tell you what the exceptions are. So when you apply these rules, apply them in order. So first, apply the rule about what's always soluble. Once you find a rule that applies, then you stop there. You don't go on to the other rules, okay? So if the first rule doesn't apply, then you go on to the second rule. If the second rule still doesn't apply, then you go on to the third rule. Let's illustrate that and actually mention the rules. Okay, rule number 1, what's always soluble? If you have a compound that has sodium in it, potassium, okay, ammonium, nitrate, nitrite, perchlorate, or acetate, any of those compounds, if any of those ions are present in the compound, then you're dealing with something that is soluble in water. You can pretty much predict with confidence that you have a sample of that compound, you put it in water, it's going to dissolve in water. So based on these, rule number 1, which of these lists of compounds here would be considered soluble? Okay, so we look for these ions right here: sodium, potassium, ammonium, nitrate, nitrite, and perchlorate. So sodium ions, let's look for compounds that have sodium. This one, it has sodium in it. That's soluble. Okay, you see anything else? That's it. Let's look for a compound that has potassium. This one, potassium carbonate, that's soluble in water. Okay, what else? You don't have any more compounds with potassium. How about ammonium? We look for a compound that has ammonium. Do you remember the formula for ammonium? It's NH4 with a positive 1 charge. So do you see any NH4 in these formulas? There isn't any. Okay. How about the next one, nitrate? What's the formula for nitrate? NO3 negative 1. Look for nitrates in this list. There isn't a nitrate in this list. How about nitrite? NO2 negative 1. No nitrites either. Okay. Perchlorate is ClO4 with a negative 1. There's no perchlorate. Okay. And acetate is CH3COO or C2H3O2 with a negative 1 charge. There isn't an acetate here. Okay, so of the list given here, based on rule number 1, we know that these are soluble. Sodium, there's acetate right there. So these are soluble. Okay, sodium acetate and potassium carbonate are soluble. Now, that doesn't mean that these others are insoluble. Okay, we can't make a decision about those others yet because we have to go on to rule number 2. So, but if you've established based on rule number 1 that something is soluble, you can stop right there. You already know it's soluble. But these other ones, you don't know yet. So let's move on to rule number 2 to see which of these other ones could be soluble or okay. So rule number 2 says, if rule number 1 does not apply, rule number 2 tells you what's generally soluble. This one says anything that's got chloride, bromide, iodide, except in combination with silver, lead, mercury 1, and copper plus 1, these are generally soluble. So if it's in combination with silver, lead, mercury 1, or copper plus 1, it would be insoluble. Sulfates are generally soluble unless it's in combination with any of these ions listed here: lead, strontium, barium, calcium, and mercury 1. And fluorides are generally soluble unless it's in combination with lead, strontium, barium, calcium, and magnesium. So based on rule number 2, classify the following as soluble or insoluble. It's the same list of compounds we had earlier, so we've already established these first two as soluble based on rule number 1, right? So let's just exclude that from applying rule number 2. We don't apply rule number 2 to those two. All right, so let's look for chloride, bromide, and iodide. Let's do chloride, bromide, and iodide. Do you see a chloride here? This is a chloride. And here's an iodide. Okay, according to this, chloride, bromide, and iodide are soluble, generally soluble, unless it's in combination with silver, lead, mercury 1, or copper plus 1. Well, this one is not an exception. It's not in combination with silver, lead, mercury, or copper. This is in combination with magnesium chloride, so you say this is soluble. How about CuI? Well, CuI is copper plus 1 and iodide with a negative 1. So that's in combination with copper plus 1. So we say that this is insoluble. So in other words, if I were to ask you to write the equation for the dissolution of copper iodide in water, you're going to say copper iodide, copper 1 iodide, solid. Okay, you have to draw a double arrow to write copper plus 1 aqueous plus I minus aqueous. You draw a double arrow to indicate that it is insoluble. But if I were to ask you to write the equation for the dissolution of magnesium chloride, this one right here, then you say MgCl2 solid. If you put it in water, I'm just going to draw one arrow to indicate that it's soluble. So Mg plus 2 aqueous plus 2 chloride ions aqueous. Okay? So that's how you would write that. All right, what else do we have? Sulfates. Let's look for sulfates. Do we see any sulfates? Okay, let's cross out CuI and MgCl2. We've already done that. Here's our sulfates right here. We got two of them. Which of these two is soluble? Most sulfates are soluble unless it's in combination with these ions right here. So this one right here, lead sulfate, is, okay, so lead sulfate we say is insoluble because that's a sulfate combined with lead, so that's an exception. Zinc sulfate, on the other hand, is not an exception, so that's a typical sulfate. It's soluble in water. Okay, and so that's rule number 2 applies to sulfates, chlorides, bromides, and iodides, and fluorides. So you got your chloride and iodide taken care of, your sulfate taken care of, your iodide. What else do we look for? We look for a fluoride. We've got one fluoride right here, AgF. Is that soluble or insoluble? That would generally be soluble unless it's in combination with any of these, but that's in combination with silver, so silver fluoride we say is soluble. Okay? So that's application of rule number 2. Now, these other remaining ones, calcium carbonate, silver bromide, magnesium sulfide, copper sulfide, silver phosphate, rule number 1 doesn't apply. Rule number 2 doesn't apply. So we move on to rule number 3. Rule number 3 says, if rules 1 and 2 do not apply, then most likely your best bet would be to say that that compound is insoluble. Exceptions would be sulfides of group 2A are soluble, and then hydroxides of strontium, barium, calcium, and calcium are moderately soluble. In other words, these are what you would call your iffy cases. They may appear to be, depends on how much you actually use for your test. Okay, so all right, we said before that rule 1 applies to these two, right? So rule number 1, and then rule number 2 applies to chlorides, sulfates, iodides, fluorides. So let's look at the remaining ones. Calcium carbonate, right here, CaCO3. Oops. Okay. Since rule 1 and 2 don't apply, so we say calcium carbonate is insoluble. We check the exceptions. It's not one of the exceptions, so it's insoluble. Silver bromide. Oh, we forgot that one. That's rule number 2. Okay. Silver bromide is rule number 2. That's insoluble according to rule number 2. Okay. What else do we have here? Magnesium sulfide. That's okay. According to rule number 3, that's an exception. Sulfide of group 2A are soluble, so that's soluble. Copper sulfide. Okay. It's not an exception, so according to rule number 3, that is insoluble. And finally, silver phosphate is not one of the exceptions to rule number 3, so you say it's insoluble. Okay, so you can determine whether something is soluble or not. You can predict based on these common solubility rules. Okay. All right. So you got several questions here that you can practice on. I'm gonna skip through them. Okay, I'll let you practice with them later. You'll see them in the homework, and you'll have videos explaining the answers. It's really just an application of the rules. Okay, since we're kind of running out of time. We have about 2 minutes left. Well, let's try a couple of these questions. How about this one? I think this is gonna be it for today. So let's try a couple more until we're done. We have to stop in 2 minutes, right? So this one, which of the following is insoluble in water? Mostly C. Very good. Okay, so this is soluble according to rule number 1 because it's got a sodium. Sulfate, and it's not one of the exceptions, so this is soluble according to rule number 2. Calcium sulfide, that's rule number 3. That's an exception, right? It's a sulfide from group 2A, so that's soluble. And so lead chloride, according to rule number 2, most chlorides are soluble, but this is one of the exceptions. All right, good. And one more. Which of the following is insoluble in water? CuCl2, Hg2Cl2, HgBr2, or calcium nitrate? Okay, correct answer here is B. This is mercury 1, Hg2 plus 2, and chlorides. Okay, so this is insoluble. Rule number 2. Okay, so which is mercury 1, chloride. Okay, this is mercury 2 chloride. That's soluble according to rule number 2. Okay, soluble, rule number 2. Copper chloride, that's a chloride. That's not one of the exceptions. That's also soluble according to rule number 2. And calcium nitrate, you see a nitrate, that's soluble. Okay, and I think we're done. Correct answer is B. All right.